Phase diagrams are graphs showing the conditions under which equilibria exist between different states of matter. And on the right we have a phase diagram for a typical substance. Notice that the solid phase of any substance tends to exist at rather low temperatures and under high pressures, and that the gaseous phase of any substance tends to exist at higher temperatures and low confining pressures. Liquids are, of course, somewhere in the middle. The critical temperature, by definition, is the highest temperature at which a substance can be a liquid. Take a look at this phase diagram again and see this blue line here. Notice that it has an arrow at the end. The red line also has an arrow at the end. The green line, however, on the right end of it, does not. It simply comes to a stop. And that location right there, if I go straight down to the temperature axis, that is the critical temperature, that point right there. We'll talk about what happens beyond that temperature in a few slides. As intermolecular forces increase, the critical temperature is also going to increase. The critical pressure is the pressure that's required to bring about liquefaction at the critical temperature. We'll talk more about that. That pressure actually, if we look at this special point right here on the graph, if we go over to this pressure right there, that is the critical pressure. So here again we have a phase diagram for a typical substance. If we draw a line down from this 1 atmosphere of pressure and between the liquid and gaseous phases, that is, by definition, the normal boiling point, the temperature at which the vapor pressure between the liquid and gaseous phases is equal to 1 atmosphere. If we go from that dotted line where it intersects the solid liquid curve, that is the red line, and we go straight down, by definition that is the normal freezing point or the normal melting point, which is the temperature under 1 atmosphere of pressure at which the solid and liquid phases would be in equilibrium. That point right there has a special name. It's called the triple point. At that combination of temperature and pressure, all 3 phases of matter would exist in equilibrium. They would change from one state of matter to the next, but the overall composition of your sample would remain unchanged. In other words, there would be some solid turning into a gas, and there would be some solid turning into a liquid, but at the same instant you'd have liquid turning into solid and liquid turning into gas and gas turning into liquid, and the overall composition of that confined sample of matter would remain unchanged. That right there is called the critical point, which is both the critical temperature and the critical pressure. The green line represents the vapor pressure curve of the liquid. The blue line represents the vapor pressure curve of the solid, and the red line indicates changes in the freezing or melting point depending on what pressure we have. Water is not a typical substance. Its phase diagram differs slightly, as shown here. For water, the solid-liquid line actually curves back from right to left, kind of pointing towards 11 o'clock, whereas for other substances, the solid-liquid line points off to the right here, kind of like towards 1 o'clock. And finally, a supercritical fluid is how we describe a substance at or beyond the critical point. We talked on the last slide that this is the critical point right here. So straight down here, there's the critical temperature. If you heat a substance up beyond its critical point, whatever else it is, it's not a liquid. It's either a gas or it's what we call a supercritical fluid, which is a liquid-like gas. It's not a liquid, it's not a gas. It is somewhere in between. So that entire region up and to the right in a phase diagram is occupied by the supercritical fluid.